Okay, good afternoon everybody. I hope everyone's having a wonderful day. So before we get to everything, I just got to make sure I get everybody into the spirit of Halloween coming up, or spooky skeleton day, whatever you'd like to call it. I just want to make sure I get all this off. Let's see here. As I lose my earpiece in here, let me just grab that. I need to make sure I hear everybody. I thought it was going to go smoother. Let me get my glasses on because I want to make sure I could see everybody. Let's get this all on. Wonderful, wonderful. Let me just get this off. Wonderful. So I hope you're having a wonderful day. So today, beautiful. I'm enjoying the chat. So anyways, what we're going to be doing today is we're going to be studying more about Turing machines today. So what I want to do is I want to remind you from last day when we talked about Turing machines, kind of the general setup for the Turing machine. So recall that we have an infinite tape that goes infinitely one way and the other direction. And we have a head that can be, I did it myself, believe it or not. I did the face paint myself. Like I said, I'm hardcore. I'm hardcore at this. I'm having fun here. But yeah, no, so we have our read head, and it can go left or right on a move. But the thing about our read write head, or the tape head, as most people may call it, the tape head has the ability to scan a cell, which is one of the squares on our tape, and it can read, and it also can write to this tape. So we're going to have to keep this in mind when we're doing this. So we're going to have this finite control that's effectively, effectively the features of a finite automaton, but it also has this basic kind of I/O of sorts where you have it where you could read and write on the head based on what state you're currently in. And we move in directions on this tape. So I thought we'd do another example here before I start ramping it up just a little bit more. We're going to be mostly spending today talking about how we could design Turing machines. So I'm going to be showing you a bunch of little tricks that you could use to design Turing machines, and we'll probably do this for the next couple of classes. So the first thing I want to do is I want to consider, say, something like this. So suppose I wanted to design a Turing machine that accepts any regular expression that looks like this. So it means that it is a 0 followed by 0 or more zeros. So just to give us an idea of what we're in for. So suppose I have as input, remember when we have our input, we have to make sure that we will know that at the beginning of this, that the initial, the tape head, sorry, I'm getting really excited here. Tape head is pointing to the leftmost cell of the input at the beginning of this process, and it will begin in the start state. In our case, I'm going to assume that the start state is Q0. And what we would like to do, yes, it is spooky input, don't you see? It's boo. Exactly. Now you're getting where I'm coming from. Wonderful. I told you it wasn't just me. Hey, so when I read in the input, it's all going to be on this tape. So remember, this comes on the tape at the beginning, so it is loaded onto the tape. And now what I need to do is I need to make sure that when this machine halts, which remember, that happens when I go on a transition, and that transition isn't actually defined. That's when the machine will halt. If it's in a final state, then I'll say, hey, look, the string is okay, except if the machine is not in an accepting or final state, then it will reject. However, like I said, it is possible for a Turing machine to run indefinitely on forever, meaning there is always that third possibility you have to be careful of. So you have to be very careful when you're designing these machines to ensure that if you really want this thing to always halt, that you have to be careful about that. So I thought we would start with this simple example just so we can get an idea of what we can do. And I'm going to build on this idea as we move along. So, because you want to be able to say, hey, look, I have 5 zeros here. This could be 0, and then that's all of my 0 star there. So suppose this is the input. The input is 5 zeros, like this. So what I would like it to do, this is just what I would like it to do, is I would like it to be able to make sure I read at least 1 0, and then allow it to read more zeros if they exist, and at that point, it better accept, right? That's sort of the idea. So let's think about how we can approach this. So one idea I have is that when I read this first 0, I better make a new state, because I want to think about it in terms of states as like the first initial one. That's when I need to read that first 0. That's maybe the purpose of Q0, is to read the first 0. Then I have Q1. Q1's job is to just simply read more zeros. And of course, if it doesn't have any more zeros to read, it better accept. So does everybody get the general gist? So I'm going to try to give different roles to the states, and then based on those roles, I'm going to perform certain moves. So I'm going to first start off with Q0, and Q0, what I would like it to do is if I see a 0, I better make it so that I can set myself up to read more zeros if they appear. So here's an idea for the transition. So I suggest that we move to Q1. So Q1 is going to be what's going to read more zeros if I have more zeros, because it could be 0 or more. So I suggest that we're going to make a move so that the machine goes into state Q1, and it will write to the 0 as 0, and then it will move right. So I'm not going to make any modifications to the input when I'm going to do this. Keep in mind, I could have designed it any other way, but I'm just going to keep it so that the input just stays there, just because this is really simple. Sometimes you're going to see, as we're going to see later, that is a very powerful thing to keep in mind, is that you can change around the input. So if it becomes useful to change these to different symbols, for example, if you're counting something, that is something you should take advantage of with the Turing machine. However, remember, like I said, you want to make sure you read that first 0, so you better not want to be able to see a 1 or a blank symbol when you start this thing up. So I must stress that the alphabet for our example here, this is over binary symbols, so 0 and 1, hence why I only have 2 columns here and the column for the blank space. By the way, what are the tape symbols for our case here? What are the tape symbols? I'll give you a hint. Look at the table. Look at the table. What are the tape symbols? Yeah, we have B, 0. Yeah, it'll be B and 0, but technically because I mentioned that sigma is also a 1, that it is possible that the input I could be provided an input where a 1 is here. So the tape symbols could consist of 0, 1, and B, just for this case. But in this particular input, it would indeed be 0 and B only, but you got to think more about it as I could give you any binary string, and its job is to tell you to accept or reject if it doesn't take that form or that regular expression. So now, if I am sitting in Q1, remember, I want to make Q1 take advantage of the fact that, hey, look, I've read at least 1 0, but I want to be able to allow it to read more zeros. Why is 1 there? Because I'm defining so if I were to formally define this Turing machine to you, I'm trying to define it so that it accepts this regular expression. But remember, I'm generally working under binary symbols, so 0s and 1s. So the input W can consist of 0s and 1s. So remember, with the definition of a Turing machine, the tape symbols is always going to be a superset of the input symbols. So if I'm telling you that, oh yeah, you could be given any binary string, then most certainly the tape symbols have to consist of all the binary symbols too. It's just that we're not going to really find them very useful for our Turing machine, because we just want to make this thing reject as fast as possible if it sees a 1. So just to be clear, so remember, we want to think about the input here. So this is the input, and I would like my binary string. So remember, my string W, the inputs, are going to be, they're strictly binary strings. So that means that the input symbols for my Turing machine most certainly have to consist of zeros and ones. But because of the definition of a Turing machine, the input symbols is strictly, it is a subset of the tape symbols. So whenever you define the tape symbols, you have to include the input symbols. That's just the way our definition works. So you're going to find that this column isn't very useful for us, but thank you. No, thank you for asking. These things are helpful for everybody because I'm trying to remind you of how the Turing machine works while we're doing this kind of simpler example. But you're going to see I'm going to kind of be using this as my starting point for designing Turing machines today. So now when I'm in Q1, I would like it so that just in case, so for example, if I were to apply that move right there, that would take me, that better take me right here, right? And what I would like it to do is keep reading more zeros if there's zeros, and I most certainly don't want it to accept if it sees a 1. But how do I know I'm home free in this situation? How do I know that I am done? Can somebody tell me when am I done? Yeah, you reach B, exactly. I need to get here. Think of it like a little game that the machine has to play. Is that, oh yeah, well, you're right here. Your job is to get me to this blank symbol. Because if I read at least at least one zero, then most certainly if there were 0 zeros for that star part, the B would be sitting right here. So it might be the case I have to read more zeros to get me to the blank the blank. Sorry, I'm getting a little excited here. So I'm just going to introduce the same move again. So I'm just going to stay in Q1 and I'm just going to allow it to keep going to the right. Just keep going to the right. If I encounter a 1, I better make sure it halts and rejects. And when I hit that blank symbol, this is the one we're interested in. I better go to Q2. So Q2 is going to be my final state. And what I'm going to do is I'm going to make it so that if, I guess it doesn't matter if I put a 1 or a, it doesn't really matter a whole lot. I guess I could technically just leave it as a B if I run into a B. I mean, I could make it a 1. It doesn't really make much of a difference. I think in my example, if you take a look at the notes, it'll be a 1 probably. But it really doesn't matter at this stage because notice that I've read all the way to the right and I've hit that blank symbol. That means that we're all good to go. So that will take me to Q2. And since Q2, I've defined Q2 to be a final state, then most certainly when it reaches Q2, it will accept. So just to make sure that we've foolproofed our design, so if we were taking a look at this, you'll notice that it's going to stay in Q1. It will move right because of this move. And then it will eventually make a move to the right here. And then it'll see that blank symbol. So it doesn't really matter what I write here because I'm already at a blank symbol. So I could just simply move the Q2 and I can accept because it will just halt. But yeah, no, so let me just make sure that we foolproof this thing. Suppose instead the input wasn't a bunch of zeros. Maybe it's 1 0 0 0. Like it's just 1 with a bunch of zeros. Okay, so we know in this case we're okay because it'll be starting in Q0, but it'll read a 1 right at the beginning and it will halt and reject. So we know we're okay in that case. And suppose I had it where, I don't know, maybe just hypothetically speaking, the 1 is sitting right here. Well, I would start in Q0, and then I would move to Q1 because I read a 0. I'd move right, so the head moves right. And then I just simply look, okay, well, if I see a 0, I move right. Oops, I read a 1. That means I better halt. And since it's not a final state, I reject. So is everybody okay with the design I've given here? So does everybody understand the idea? Is that I want to take advantage of these states to help me encode some information about what I'm going to do with this Turing machine. So the state is going to help me kind of build structures that allow me to describe when I move right and left. And these are sort of going to have meanings when I talk about it when I design the Turing machine. So sometimes, like later on, I'm going to show you how you can make a loop. So it's going to be kind of fun. But yeah, is everybody fine with this example? Give me a thumbs up if we're all good with this. Excellent, excellent. Okay, good, good, good. Now, don't be shy. That's why I'm walking us through this carefully. But yeah, so this example is pretty nice. It's pretty nice. But I would like to give you a flavor for what a Turing machine, like when people talk about Turing machines, there's a bunch of different kinds of Turing machines that usually are called different things because they have different purposes. Because you'll notice that the way I talked about a Turing machine last day, I was talking about accepting and rejecting strings, right? The technical term for this is recognizing strings for a given language. So I'm just trying to determine if the string belongs to that language, usually. That's what a recognizer does. I'll talk more about that if we have time after this. But a lot of the time when we design programs, we often wanted to have it where the machine, it gives me output from input. So for example, if I have it where I give you, say, an arithmetic expression, and I would like to add two numbers, I would like it so that it will output me the result of that expression, right? We do this kind of stuff all the time in computer science, right? So I would like to have some way of talking about that in a nice and easy fashion. Now, the thing that's very interesting about this is that this notion of having it where we care about the output that's sitting on the tape. What I mean by that is we're going to modify the input on the tape so that it reads as our output. This idea actually stems all the way back to when Alan Turing was talking about what he was calling automatic machines. He's seen and conceived of the Turing machines as these things that they're integer valued functions. So very often Turing would be interested in certain operations that these machines would be capable of. So I want to give you a flavor for how you can go about studying this type of Turing machine. It's what we call a transducer. So just meaning take the input, give me output. So take it from one medium to the other. That's where the name comes from. So suppose I give you multiple inputs. So I want you to think back to, like, say, if you're thinking about programming or algorithm design just generally. Very often you'll have it where you have multiple parameters that are inputs to your given problem. So I just want to give you that overview idea, is that we have some problem, you may have inputs for it, and these are what we classify as like the problem instance. Well, we can think about this more as like the inputs more broadly. And we can encode this information on the tape, where what we do is we introduce what we call separators or markers. And you end up with blocks like this. So you can this is one way you can do it. Of course, you can encode these things in binary as well. I'm just going to use unary to keep things simple. So the idea is that I'm going to have it where I'm going to have all of these blocks, and they're going to be separated by these markers, which are I'm just going to use ones for simplicity. And then I'm going to have these integer size blocks, which are going to all be zeros. And these are going to be the number written in unary. So for example, here I have 5 zeros. That represents 5. Just like the second block here has 3 zeros in it. That means I'm representing 3. So this is just one very simple way of representing numbers or multiple parameters on the input tape. So like I said, if you want to go wild with this, you could technically represent them as binary and use different separators. Like technically this is pure binary, it's just zeros and ones, but you hopefully get what I mean. It's that these blocks could consist of zeros and ones, which naturally would make sense when you're thinking about an actual computer, which encodes its information using bits, right? So I'm just going to keep things pretty basic like this, just for the sake of our conversation here. But we call these things, like I said, transducers. And typically we just ignore the final states. So usually when I define a transducer, I will not tell you what the final states are. All I do is I care about when this machine halts, that the output on the tape matches what I think it should. So I give you some idea. So I'll give you a couple examples of this today. So the first example I'll be doing is addition. So imagine I want to have an input like this, and I want to know how you add the two numbers. So we're going to start off with that. Does everybody have the idea of what we're talking about when I talk about a transducer? So just think of it like the input's going to be sitting on the tape. Your job is to convert the input into output, and that output is what I'm looking for. So for example, if I'm adding two numbers, the numbers will be encoded in this case using unary, where I have these separators or markers. So I'll have two of them, and my goal is to add the two numbers. And then, so when I'm done this process on the tape, it better read the sum of those two numbers. That's what I mean. So I'm not going to be caring about it accepting or rejecting. I'm just going to care that it halts. Hopefully that's clear. So I'm going to be kind of taking a step back from our notion of acceptance, and I'm just going to care only if it halts or not. I just want to give you a flavor for different kinds of Turing machines that people give these names for. But this is one very useful way of thinking about a Turing machine, because very often we don't think of the problem very much like it's just, oh yeah, no, it accepts into the language or rejects. Sometimes we actually have it where we just want to have some output that gets produced from input. So I'm just trying to give you some examples of that. Okay, so let's do our first example here. So I thought I would start it off with nice and simple. So something that you would think is rather primitive, but something that once you see it, you're like, okay, that's kind of neat. I'm hoping I'll stir that curiosity in you to think about what you can do with a Turing machine. So my goal here is I'm going to show you a couple of things that you think are pretty basic things that a computer does. So I'm going to first think about addition. There's other ways you can go about this, depending on how general you want to describe your addition. So first, let's show how to perform addition. So what I'm going to do is I'm going to assume the numbers are in unary separated by a marker. So I'm going to assume they're in unary. So if you're not familiar again what unary is, if you know what binary consists of a set of two symbols, right? Unary is just where you can think of it just as a single symbol. So for example, a bunch of zeros or a bunch of ones, like that's all you get, just one symbol. So the numbers are going to be written in this fashion. Then I'm going to assume input is given in the form. So this is the form it's always going to come at you at. So you don't have to do any error checking or anything like that. Just assume it's going to be given to you like this. It's going to be given to you as 0 to the m, 1, 0 to the n, where m and n are non-negative. So that means that I'm allowed to have 0 zeros on one of these two sides. And the output. So when I'm done this process, the output better be the result of the sum. The output should be 0 to the m plus n, like this. So notice that the separator cannot be here. It's simply that it has to be the sum of the number of zeros on both sides of the separator. So let me, now the great part about this is that there's actually, if you think about it, this is the input and that's the output. So does anybody have any ideas of what I could do with respect to a Turing machine? I want to design a transducer that takes this on the input tape and then leaves on the tape this output. Any ideas? Yeah, you want to remove that 1, exactly. Yeah, so our goal is to get rid of this 1. If I can get rid of the 1, we're okay. So that's our goal here. But the great part is, once you think about it that way, oh yeah, that's really what addition is in unary. Is that kind of neat? So fortunately, this is simple, right? So we need to do two things. So now remember, I can kind of think of it in one way. So suppose I have it where I have this 1 and then a bunch of zeros. Now, one way you can view this, by getting rid of this 1, I can shift, if I can shift all the zeros by 1 to the left, then I should be able to accomplish this, correct? So that's what I'm going to be trying to do, is I'm going to try to perform a, no pun intended if you're thinking about more of a system side of this, I'm going to left shift all of the zeros in one direction to the left. So I'm not going to bit shift them, I'm just going to left shift them. But it's the same idea, just it's not literally bit shifting because bit shifting's on binary, right? I'm just going to shift them over by 1, shift the zeros. So I'm going to say, so my idea is I'm going to remove the 1 by replacing it with a 0. Now, if I do that, does anybody have any ideas of how I can effectively perform this shift that I'm talking about? Does anyone have any ideas of, now remember, all of the symbols are zeros. So it doesn't have to be anything fancy-pantsy. Yes. So that's pretty much the idea, is that we're going to go furthest to the right, get to that last 0, the one that would be the last one for this right part, and we'll replace that with a blank, which will effectively do my idea of shifting them all to the left, but it's not literally shifting them to the left. I'm just making it so that it acts like that. So that's wonderful suggestion. Wonderful suggestion. So I'm just going to replace the final 0 with a blank. Now, if you think about it that way, this actually isn't that different from the example I just did previously. It's just that I just need to think about it a little differently, just a little differently. So I'm going to draw a transition table, and I'm going to walk you through how this is all going to come together, and I'll try to keep a picture along with us while we're doing this. So I'm going to have my states. Now remember, because I'm given zeros and ones, the tape symbols are 0, 1, and a blank. If you find yourself looking at this after class, I'm going to include in my table a short description of what each of these states means. So I'm going to describe them verbally like I have been here. But I will include in the notes, if you're finding yourself after this staring at them like, why is it that? I'm going to include a little column there to help you remember what each state is if you need to look back at this after, okay? So what I'm going to do is I start off in Q0. That's what I would like to do. So I'm going to assume that the start state is Q0. So I'm going to assume that this is the start state, just to be clear. Remember, it's a transducer, so we're not really going to care about any final state. So what I'm going to do is I'm going to start off by trying to get myself over to that 1. So the first thing I'm going to do is just move right. So when I have my input, so suppose the input is, say, 0, 1, 0, 0, 0, with blanks on both sides. And say it keeps going on and on and on both sides of my input tape. So what I would like to do is move right so that I can reach this 1. Keep in mind there may be multiple zeros. Now, when you look at this, the goal in our example here is I would like to get the result of 4. I want 4 zeros, right? So if I start Q0, Q0 is going to start right here. If I read the 0, I go right, and that'll take me right here. So if I'm Q0 right here, then I go right here. I would like it to go to another state where it's read this 1. But to finish off this, I'm going to make it so that when I reach the 1, I turn that into a 0. So I'm going to write the 0. So that task is done. And I don't have to worry about the blank at all, because I can guarantee you, because of the way the input is given to me, that I will see this 1 always. This 1 will always be there. So when I read this 1, I'm going to turn this into a 0. And then it's going to become, so it's in state Q1. So Q1's job now, so Q1, what I'm going to use Q1 to do is it's going to get me all the way to the end to find that last 0, the one that I want to replace with a blank. So that's what Q1's job is going to be for me. So I'm going to have Q1. So if ever I read zeros, because I'm going to run into more zeros, right? Possibly. After I've moved right, because remember, this will make me move right. So I'll be right here when I'm in Q1 after I've written that 0 down. So I may read a whole bunch of zeros at this point. So what happens? Well, I want to make sure I keep reading in those zeros and moving to the right. Eventually, after a whole bunch of these moves to the right, I will eventually hit right here while I'm in Q1. Actually, let's think about this. Let's see. Yeah, that's what I thought. We need to find the last 0, but to find the last 0, it's sufficient to just find where the first blank is. Why? Does anybody have any ideas of why I would stop right here as opposed to here? The answer is surprisingly much simpler than you might think. It's just think about what the Turing Machine's capable of. Yeah, so the reason why I have to stop here as opposed to there is because I don't know that this is the last 0, right? There's no way I can know that without evaluating this next symbol. At least from our perspective from moving to the right. So this will ensure that I'm at that last 0 if I move left from the blank symbol. So that's what I'm going to do, is as soon as I see that blank, it's going to move left, and that'll sit me right on top of the last 0. So I'm going to make a new state called Q2, and I'm going to move to the left. So when I do this, so when I read that blank, I'm just going to leave the blank alone. I'm leaving the blank alone, and then I'm just going to move left, and that'll bring me right here. So all I'm going to do at this stage is now all I'm going to do, nice and simple, is if I see a 0 right there, I better turn that into a blank. So if I read a 0 at that spot, then I most definitely need to replace it with a blank, right? So that's really it. So then I have Q3. Q3 doesn't do anything. So Q3, once it reaches Q3, there's no valid moves at that stage, and it will halt when it attempts to read the next cell. So are we okay with this example? So I've shown you here how you can take, given in unary, 2 numbers and add them together. Do you see how the ideas that we did earlier sort of translate nicely here? So we use the fact that we can move across this tape, and we encode that using these states to help us determine if we've reached where we need to go. And our goal, of course, after that is just to simply see what happens. And if we hit where we need to go, then that's when we move to another state. So we can take advantage of this to design things, for example, like effectively loops. So for example, if you want to scan through across the tape to make it check something, you can take advantage of the fact that if we encode these states in a way that's like this, you can always make it so it loops back to, say, for example, Q0, which is what we're going to do in a little bit here. So I have one more example of a transducer. Just for the sake of time, I'm going to ask you to take a look at it in the notes, but it's an example for copying. So if I give you a string in unary that looks like this, what it's supposed to come out as, so this would be the input. The output better look like it written twice like this. And a lot of the strategy involved with doing this is actually quite similar to this, except you can take advantage of the fact you can read those input symbols, and you can take advantage of their count. So what you do is you try to count them. So in this example here, this copying one, when you take a look at it, I want you to think about how this occurrence of counting pops up in it. I'll give you a basic idea of how it plays out. So essentially what happens is you want to make sure, if you want to double up the number of zeros there are, say for example if we had this one right here, the idea is essentially this. You start off in Q0 and then you clear out all of these zeros with another symbol. Say for example C. And then what you do is you work your way to the right, and then every time you are at a cell at this stage, what you do is you turn this into the 0, and then you go back here and rewrite this back to be a 0. And then you move forward after you've read a 0, and you work your way back and forth, pairing up each C with a 0. So you go left and right, left, right, left, right, left, right, until you have no more C's anymore. And that's generally how you can do basic counting with the Turing machine. And this technique, we'll see an example of this actually in a little bit here. So are we okay with our addition example? So I'll recommend you take a look at this. It's a pretty useful thing to think about. If you think about it carefully, I'll let you think about it, is we've seen how we can do addition in unary like this, and I mentioned that there's this way I can just copy it like this. Can you see a way that maybe you can do multiplication using both of these? I'll let you think about it. Because of course, if you have a way of adding, then you can think of adding as repeated additions, right? Multiplications as a series of series of additions, right? So you can think of it like copying, but copying several times, right? So you just need some way of knowing how many times you need the copy, which comes back to the same trick I was just mentioning here about where you replace all the multiplicities of a number with a special symbol and then you try to pair them up. But I'll show you an example of what I mean by this pairing up business. So let me do another example. So here's an idea. Just because I want to show you that this Turing machine business is not really at first we've seen some kind of, I don't know if you would be convinced by these examples up to this point that this thing is capable of all sorts of neat computational tricks. You will certainly have seen some examples where we've done basic arithmetic, right? Like very basic arithmetic or basic operations a computer might do. Now, I want to do another example, but I want to pick on an example of something I talked about another lecture ago. Like I think it was a couple lectures ago. If not, it was like a lecture ago. I'm going to design a Turing machine for a non-context-free language. So I'm going to design a Turing machine for a non-context-free language. So I'm going to pick on one of the examples that I mentioned the other day, and I'm going to show you how you can design a Turing machine for it. And it's actually going to use a lot of the ideas I've just described up to this point, which should be quite surprising. So the language I'm going to consider the following language. So A to the n, B to the n, C to the n, where n is greater or equal to 1. So this right here, remember this is not a context-free language. So you most certainly won't be able to give me a PDA that will describe it, or even a context-free grammar that could describe it. So I'm going to show you that I can use a Turing machine to accomplish it. But to do it, I'm going to actually start off with a simpler language to illustrate the idea, and then I'm going to show you how all I have to do is just nudge the idea one step forward to get a Turing machine for this language. And the way I'm going to do it is I'm going to start with the following language. I'm going to call the non-context-free language L2. I'll start with L1. I'll call this one L2. So L2 is just going to be A to the n, B to the n, and greater or equal to 1. You should know that this language is what? What is that? What language? What kind of language is this? What kind of language is that? Yeah, it's context-free. Exactly. So what I'm going to do is I'm going to design a Turing machine first for this, and it should naturally give you the idea of how we're going to approach this one. And I'm going to tell you up front, like when I first seen this, I was like, wow, that's actually quite surprising how easy the idea jumps from one to the other. That's why I wanted to show you this. So here's the idea. Here's an idea. We're going to match each A with a B. I'm going to underline the A's and B's to make this a little easier to read. With an A and a B by marking each with an X and a Y, respectively. So this is where things are going to get a little... like I said, I'm going to tell you about this matching strategy when it comes to drawing out these Turing machines. Is that if you ever want to count things to make sure that they are of equal amounts, this matching approach I'm describing to you is very useful. It's the same one I mentioned just a moment ago for that copy example. But you'll see how this is going to play out here. So I want to just before I write anything down, I just want to give you the idea of what I'm trying to think about here. So I want to I'm not going to get too formal about it yet, but I just want to give you a flavor for what I'm trying to do. So suppose I have AA, BB like this. So what my idea, this is the idea I'm going to propose to you. My apologies, I tapped the mic. So when I see an A, what I would like it to do is I would like to replace this A with an X, and then I would like to go right until I see a B. So I would like to go right until I see a B, then replace this B with a Y, so that I have an X and a Y, one for an A, one for a B. Then I would like it to do is zigzag back and forth, so that when it sees the next A, which will be the first one that appears after an X, I would like to turn this into an X, and then I want it to zigzag all the way back over here to the first occurrence of a B and turn that into a Y. And then I would like it to zigzag back just in case there's maybe more X's that I need to mark. And then finally I would like it to zigzag all the way back to a blank space. And if it hits this, then we're done. So the idea is I would like to go back and forth trying to see if I can pair up every A with a B. And whenever I make a pairing like this, I'm going to mark an A with an X and a B with a Y. That's going to be generally the big idea I'm going to use here. So we're going to just zigzag back and forth upon reading each A and B. So that's going to be kind of the general idea that I'm going to be taking to use here. So I'm going to try matching each A with a B. And the goal is when I design this machine, I would like to have it so that if it fails to match an A with a B, or there just are a bunch of A's that I haven't accounted for, or there's some B's that I haven't accounted for, that my Turing machine will certainly halt if I don't get that process to match up nicely for us. So here's how I'm going to encode these states. So this is where I'm going to introduce you the idea of how we can encode like a loop. So this is kind of like a Turing machine basic kind of loop you can think of. So here's how I'm going to do this. I'm going to have Q0 is going to represent, it's going to be ready for the next match. So whenever I go to Q0, that's essentially where I'm going to set myself up to do another one of these matchings of an A and a B. So this is going to be my setup for the loop. And then I'm going to have a state I'm going to call QA. QA is going to be going right. It's going to be going right after reading an A. And this is, of course, after marking with X. Then I'm going to have a state quite similar to QA. I'm going to go and I'm going to say going left. Because remember, I wanted to go back and forth, right? So I'm going to have going left after reading a B. So this is right when I encounter reading a B, this is how I'm going to switch over to this one. Going left after reading a B. After marking with Y. So this is after I mark the B with a Y until we see X. Because I would like to be able to get back to Q0. So when you look at this, the way I want you to think about it is, like, this is one way of thinking about it, of course, is that I'm going to have it, so I'm going to set up this, try to get this match to work up. This is after I start up the matching process. This is after I found a complete pairing of an A and a B, and I want to work my way back here, and it will repeat this process over and over again. So that's why I'm saying it's like a loop. So I'm going to use these states to effectively encode that information. And then I'm lastly going to have QR, which is going to be, its job is just to sweep over the input just to make sure I accounted for everything. As in, there are no straggling symbols that I have not matched. Check that all input has been matched. And then I'm just going to have a final state. It's nice and easy. I'll just call it QB. It's going to be a final state. So this is my description of what I'm going to design for you. This is what my Turing machine is going to do at the high level. So has already got generally an idea of what I'm going to do here. So remember, I'm going to start off here. I'm going to make it so I can go all the way to the first occurrence of a B after I've marked an A with an X. And I'm going to go towards the first B. My counter, I'm going to replace it with a Y. Then I'm going to work my way back to where I see the first X I'm going to run into on the left. I move one to the right, mark that A with an X, and then I keep this process going back and forth until all of the B's are now Y's and all of the A's are X's. And at any stage of this process, if I fail to find a B for an A or an A for a B, then this process will in fact halt and reject. That's what I'm going to do. So remember, I'm going to start with this simpler language, and then I'm going to show you how you can very simply tweak it to get this one. I want to make it so it accepts on that language. Does everybody understand the game plan? So I'm going to yes. Yeah, so for every A there has to be a B, exactly. They have to be equal numbers of A's and B's, and the A's always occur before the B's. Yes, exactly. So I'm just going to show you how I design it for that one, and then I'm going to show you how you tweak it ever so slightly to get this one. Because once you look at the idea I have on the board, you've seen how I do the zigzag process. You can almost think of it like, hey, look, maybe I can add another symbol, like I can make it keep going to the right and just make this zigzag process just go a little longer. That's where we're going to be going with this. So what I'm going to do is I'm going to define the Turing machine for us, and then I'm going to draw you the transition diagram, and then we're going to wrap things up here today where I'm going to modify the transition diagram so that it works for the non-context-free language that I've presented. Because I've got to wrap things up here. So let me draw, well, I have to define the Turing machine for you. I'm going to do it with a transition diagram this time. So I'll say here is its Turing machine. So I'll let T2 equal, so it's going to have Q0, QA, QB, QR, and Q capital B. You can see I've kind of given them names, like this is for the A's, that's for the B's, this is to go right for the last checkup, and this is for a blank. So when I counter the blank, that's when I know I'm going to be done. And then I'm going to have all of my input symbols are just going to be A and B. Then my tape symbols, I'm going to have A, B, X, Y, and the blank. Whoops, curly brace. We want a curly brace there. Delta, Q0, blank, and F is going to be Q capital B, or Q blank. I'll call it Q blank because it sounds fun. So here's my transition diagram. So where delta is as in the below, sorry, this is as delta as in the below transition diagram. That says below. This is a beautiful illustration of why words are melting on my screen. Transition diagram. So here's my transition diagram. So I'm going to have Q0. So I'm going to start it up. And then I'm going to have it where I have QA. Sorry, QA. I was tempted to write Q1, but it's QA. I'm just going to keep things simple, and then I'm going to add in more transitions as we move along. Actually, I'm going to draw this one a little lower down, just because I'm going to need a little bit more space for this one. I'll call this one QB. And QB is going to come all the way back over to Q0. Remember, that's our loop. And then I'm going to have it so that it comes back down to QR. And then it's going to go to this final state that's Q blank. So I'm going to add in a couple of small things here. So I'm going to have a couple loops here. So I have Y, Y, and I have left. I have A, left. And then I'm going to have on this one, Y, Y to the right. And I'm going to have A. When I read that A, I better move to the right, keep the A there. But what I'm going to do is I'm going to start this off by having it so that when it reads an A, it replaces it with an X and then moves to the right. And then it's going to keep skipping over A's and Y's until it hits that B. So that's what this move is going to represent. So I'm going to have B, then I'm going to have Y, where I'm going to replace the B with a Y, and then I'm going to move left. So this is what's going to cause that zigzag to happen. So this is the one that starts it off going to the right. This is the one that starts it going back to the left. And then I keep going to the left until I hit what? An A. X, X, and this is what's going to get me started back to reading the next A. So when I hit that X on the furthest left side, that I first encounter, just to be clear, this is the first X I encounter when I'm moving left. When that happens, I better move right one because there's going to be an A there if there is one. Then, lastly, if I keep doing this process, zigzagging back and forth, I'm going to have it eventually be where the next symbol won't be an A, it will be a Y. Because remember, I have to pair all of the A's with the B's, and that naturally means that all of the X's will be matched with Y's, meaning that when I move over to get that next A, it'll be a Y sitting right there. So I'm going to get a Y, and then I'm going to, of course, transition from, I'm just going to keep the Y's there, and I'm just going to move right until I get to the blank. And when I see a blank, I keep the blank there, and I just go to the right. So this is our Turing machine drawn as a transition diagram for this language. Now, is it okay if I take one more minute and I can show you how to simply change this to be the non-context free language? I assure you it will only take me a minute to do it. Is that okay, everybody? I know it's Friday. I know. Aren't I terrible? I'm sorry. How about, do you want me to, does anybody not have time for me to quickly show you how to change this to make it so it works for the non-context free language? Because I could quickly show it to you and then I'll leave you everybody here and I'm going to go have a bootastic time somewhere else. Yeah, if we're okay, I'm going to quickly just add in the one little bit to this. So this would be the one for L2. So like this is L2's Turing machine. Naturally, that's great, but I would like to show you how you get the last one. Now there's more details about how I came up with the design in the notes, But I'm going to show you how simple it is to change up this Turing machine design. Just because yeah, you're going to do the exact same thing again. So remember, yeah, exactly. So remember, I have A's, and then I may have B's, and then I'll have C's, like this. So when I mark an X on an A, I move right? And then I hit a B, I make a Y. Now, instead of going left, instead I go right. I keep going right now. Instead of going left, I keep this process going where I replace a C with maybe a Z. And then that's when I go back to the left. So notice this really is not very much different really at all. Is that wild? So I'm just going to quickly show you how you tweak this. Just a very simple tweak that's needed for this. I'm just going to add in a couple extra moves on some of these states. So all you do is you add in a new state over here. I'll call it QC. That's for the same purpose you would think of that we had earlier. So I have QC, and this will be where I read the C, and I replace it with, oh yeah, I need a Z as well here. So another tape symbol I'm going to need is Z. So I put Z in the tape symbols. So what am I going to do? Now I have to move past all of these Y's and Z's and B's. And so I have to go all the way back to the left to see if I can run into a possible X. So let's see here. So I would need Z, reading a Z, then I see the Z. Sorry, I see a Z, I write a Z. I have a B, I write a B. I have a Y, I read a Y, and I go left. All of these I'm going left, by the way. Basically, go through all of the ones that could, that's what I'm doing. I'm just going to go left this way. And then I just need to add a couple small tweaks here. So first, this loops back the exact same way we had it before. Except now I have to make sure that the first thing is that I have to change this up, because now that process is being done by QC. That going back left is QC. That's QC's job. So now this will allow me to proceed to find the next C. So I would have Z, I get a Z. I don't change it, I just go right. If I have a B, I just keep the B there and go right. And here, I think that's the exact same. Yeah, that hasn't changed. This is good. That's good. And I have to just account for the Zs, because when I hit the first Y, which is something I'll still guarantee, I'm going to have it where I, of course, going to have to make sure I can get past those Zs. And really, that's all the modifications you need to get L1. So this is the Turing machine for L1. So that's the one that matches the A's and B's and C's. And notice how all I did was I took a simpler idea and I showed you how, with just a small change to how that loop works, that I can get an actual Turing machine that actually recognizes a non-context free language. Is that wild? So when I come back next day, I'm going to start talking about the language of a Turing machine and providing you some more interesting ideas around the Turing machines. So my hope is that I'm starting to convince you that this Turing machine, even though how simple it is, it actually does compute all sorts of things that a general computer is capable of. So that being said, I want to say thank you very much and have yourself a beautiful day and have a good weekend too.